Hi, this is Wendy. Greeting to you all from Eastern Washington, USA. I hope you have been staying well and safe. And thanks to everyone joining this session. In this two demo paper talk, I will share our thoughts about a tool implementation on a static interprocedural data difference analyzer for real-world C programs. As we know, static data difference analysis plays an important role in software quality assurance, such as impact analysis, targeting obtaining the impact of changes in the deployed products, or taint analysis, aiming at detecting the behavior of the unsecured data. Unfortunately, it is hard to find a static data difference analyzer to work with right now, as existing frameworks or tools for this target commonly suffer scalability challenges, especially in industrial-scale software systems. A conservative static data difference analyzer contains features such as flow sensitivity, context sensitivity, field sensitivity, and so on. It will be very CPU and memory consuming if all these features are implemented in a tool. And this will be seriously hamper its effective application in large industrial-scale software systems. A common strategy here is to get a balance between precision and scalability. Reusing or weakening a property, for example, context sensitivity, can make the algorithm become much more efficient. Then we optimize the accuracy in some extent and the save time or memory cost. In this paper, our goal is to develop a static interprocedural data difference analysis tool that scales to industrial-scale software system with a practical cost-effectiveness trade-off. To evaluate the tool, we solve a typical short-sync problem, that is memory leak detection. The results indicate that our tool performs well in both time and memory efficiency, and our tool is able to detect practical vulnerabilities. In general, data difference analysis in PCA is finished in three main steps: Anderson-based points to analysis, core graph construction, and data flow analysis based on the classical fixed point iterative algorithm. The algorithm applied in our implementation are flow, context, and field insensitive. As mentioned above, abandoning these properties will reduce the accuracy of PCA. However, PCA obtains ability in analyzing industrial-scale software. Then we contribute to main optimizations in PCA. The one is partial corpus analysis. It targets to improve the precision of results caused by the imprecise algorithms. And another is the integer encoding. We encode each def use pair into a unique ID. The memory usage reduced from 16 bytes to 4 bytes for each pair. It helps reduce 75% of the peak memory usage in the classical iterative data difference analysis. PCA features a partial corpus analysis during the interprocedural data difference computation. It reduces the effects of false positives by providing partial flow sensitivity and function level when computing variable definitions and use on the unprecise point-to sets computed by Anderson algorithm. The depth of corpus is user customer measurable, but recommended value is 6 to 8. Too big value will cause path explosion and affect the tool's performance. In given example, we get the variable FB's point-to sets is S, B, and A by Anderson algorithm. When we compute the variable FD's data flow fast along corpus from main to function B, we can program the variable A on this path so that the precision is improved. On the other hand, with this reduced set, the iterative data flow analysis can coverage faster. As an example application, PCA Man is implemented based on the interprocedural DDG and SIGSOFT from PCA. PCA Man addresses static memory leak detection on a source sink problem. In this application scenario, PCA Man considers each allocation set as a source and each free set as a sink. Through checking reachability from a source to each corresponding sink against data and control flow conditions, PCA Man can capture potential effects. Briefly speaking, if a source cannot reach any sinks along DDG, it must be never free. Otherwise, PCA Man will check SIGSOFT reachability. If existing at least one SIGSOFT path, a source cannot reach any sinks by DDG, then it is partial leak. PCA Man is only one application case. Other extensions such as taint analysis, impact analysis can be built on DDG and SIGSOFT generated by PCA. To validate the effectiveness, we evaluate PCA via PCA Man against SVF Sabre as baseline. We test both PCA Man and Sabre on Spec 2000 benchmarks. PCA Man found 161 leaks with 9 false alarms in about 114 seconds, consuming 2.16 GB memory. In comparison, Sabre found 20 leaks with 8 false alarms in about 112 seconds, consuming 6.44 GB memory. As Sabre considers not leaking the heaps objects that flow directly into global variables. Defects associated with global variables are specially flagged in the table. Generally, excluding the global variable case, PCA Man appears to be very close to Sabre in effectiveness. To evaluate efficiency, we run both tools against industrial scale workload manager, SLUM. Here, we demonstrate the memory usage and the time cost of both tools on all executables in SLUM. Looking at the performance of PCA Man alone, PCA Man can finish analyzing the whole program containing total 4,079 kilolog code in 40 minutes with peak memory usage 2.8 GB. While being compared to Sabre, PCA Man used 68% of Sabre's time cost and 24% of Sabre's memory usage. So PCA Man's performance is better than Sabre's. About the effectiveness, PCA Man reported total 21 leaks in which 10 were associated with global variables and 4 were manually validated to be defects, including 2 partial leaks and 2 level frees. By contrast, Sabre reported 10 leaks identified as false positives. So PCA Man has capacity to detect real-world defects in industrial scale software. Based on these experimental results, we summarize a common strategy for implementing a practical tool. In general, algorithms with higher precision assurance may also be more consuming. They are usually unpractical against large-scale C programs. Our strategy is to build an unprecise and much faster tool. Then, based on this efficient tool, we conduct some optimizations to improve the precision and immediate consumption, so we can get better cost-effective trade-off. And the PCA was implemented following this strategy. This is really a quick talk. For more details, you can check out papers online. Now I will be answering questions in our Q&A and discussion session. Thank you for your time and attention.